In the last class, I had briefly reviewed liquid phase sintering. Let me round up the review of the sintering process by talking today on the factors that affect solid state sintering. It is true that in many cases we resort to liquid phase sintering to achieve better uniform grain structure, faster densification. But as I had stated earlier, in most of the cases we have to do subsequent grain boundary engineering so that the amorphous phase between the grains is converted to a crystalline one. Sure enough, we do it, but in many cases formation as liquid phase is not desired, as that would give rise to multiple phases. And in such cases we have to resort to pure solid state sintering. So what are the factors that affect solid state sintering? The first thing is temperature. In a solid state sintering, we have got powders packed, and what do we do? We heat it at a higher temperature. What does this temperature do? It improves diffusion. As I had covered earlier during this course of review of sintering, there are two principal types of sintering mechanism that are operative during solid state sintering. One is the grain boundary diffusion and the other is the bulk diffusion. It is the bulk diffusion which is affected more by the temperature. I will not go into the detailed mechanics of it, detailed equations, but it would be suffice to say that increase of temperature leads to increase of diffusivity and hence enhanced sintering. The next factor, that is this is, I would rather say, one of the biggest critical factor, is better packing of the grain body. Means in the grain body which is the unfired body, that is a body obtained either by pressing or by any other process whereby the raw powders are cast in the form we desire. In that green body, the particles should be packed very efficiently. In fact, it is very desirable to have uniform packing. Like say, it would be very desirable if we can have spherical particles with a packing something like this, which is the maximum packing. Here we have got 74% filled space and the balance 26%, which are these spaces, this is vacant. This is ideal. We do not have this ideality in most of the cases. However, yet, we would strive to have as much packing as possible. Let me draw this in another form. Same diagram, but now the particles are packed in this fashion. You can see that the pore sizes are much more larger than in this case, and as a result what happens is we require more force to close these pores so that we can ultimately have a sintered body which looks like this with no pores. It is easier to come to this from here. It is easier. It is tougher to come to this state from here because these pores have to be filled up. So, we require better packing. Secondly, uniformity of the microstructure in the grain body. I will dwell on this. The next point is when I talk of on a subsequent narrow particle size distribution. Here I have brought in the third term, narrow grain size distribution. What do I mean by it? If I am drawing a diagram, particle size, let me put it on a log scale. This is 1, 10, 100 and 1000. This particle size was originally in micrometers. And this is weight percent of particle in size. Normally what we have is particle size distribution even in the most ideal cases, a wide distribution of particle sizes. It means we will have some fraction of particles, maybe 10%, which is as high as say 1 micron or 1000 microns. These are micrometers with 1000 microns. Most of them will be somewhere over here, which is roughly 30 microns on a log scale. So while we may have, it is true, we may have 30 micron particle sizes. Let us presume these are all 30 micron. We will have ones which are very big, 1000 micron, ones which are very small, 10 micron. What will this lead to? This will lead to variation. If I come back here to this diagram, I will not have this sort of packing anymore. I will have somewhere, I will have, if I have got this, I will have large pores. It's true. So what we normally desire is a reasonably narrow size particle distribution. This is a good reasonable one, because if at the FWHM this is a half height, about 50% of the particles are over here, while the rest are scattered. So it would be ideal to have a narrow particle size distribution. If I could have this, it would be far better. But then what happens is, these very narrow particle size distribution again ensures that yes, they have got a uniform particle size, diffusion distances are constant, so there won't be any variation in the grain size. It is not expected, at least. But then again packing goes down. I will come back to this when I talk of 4. Now here I talked of narrow particle size distribution. So let us presume that we have got say 0.1 micrometer fine particles greater than 80% are of the order of 0.1 micrometer. I have got 10% say in the range 0.1 to 0.2 micrometer, and for brevity's sake let me assume I have got something from 0.08 to 0.1 micrometer. So I have got a very fine particle size distribution, very small particle size distribution. As I said, if I have got this, I will not have uniform packing. Again, to reiterate, I will say draw this diagram. Let us forget the scale. Whatever be the scale, whatever be the diameters, be it submicron, be it nanometer, or be it micrometer, this space is vacant, finished, end of the story. So to avoid this, especially in coarse systems, we add this grain size and also the finer grain size. So, we talk of narrow particle size distribution with caution. Now, the last point I have said, agglomerate free fine powder. Why did I say it? As particle size decreases, say to 0.1 micrometer or 100 nanometers, what happens? The surface to volume energy, this goes up. Let's say we have got 10 nanometer particles. The surface to volume energy has shot up really high. And if we talk of still finer, the surface to volume energy is really very high. So, in this ultrafine range, which the fashion word today is nanotechnology, in the ultrafine range, our biggest enemy is keeping them agglomerate free. This agglomeration occurs simply because the particles are so fine, their surface energy is so high that they tend to agglomerate. A schematic diagram would be, if we assume all of these are say 10 nanometer particles, each of them are 10 nanometers, they would form this agglomerate because they have to reduce their surface energy, and hence we will have this agglomerate over here. So, if in a green body, let us say in a 2D scale, we have, or let me draw a 3D scale. We have used say 10 nm particles to make this green body. There is a very high chance what we will see is agglomerates of 10 nm particles. And the result is, because this agglomeration is uncontrolled, the degree of porosity is very high. And the uniformity of sintering which we so desire from these ultrafine particles, it is generally lost. Later on during the ceramic fabrication and processing methods that I will show is, in order to beat the system or work with nature, not against it, we devise various means. There are various techniques we use whereby these submicron or nanometer level particles, they can be used for fabrication of very dense bodies with almost 100% densification. The other thing is, people have chased these submicron particles thinking that this could give us ceramics with ultrafine microstructure. But achieving ultrafine microstructure so that the strength properties are increased, that has also proved very elusive today. If we could have sintered say 10 nanometer particles without causing grain growth, we would have ceramics which would be as flexible as a paper. The reason simply is this, that if the grains are very fine, then instead of a large grain, we would have very finer grains. each of the grains could bend with respect to the other by thousandth of a fraction of a degree, and ultimately we would land up with a flexible ceramic. Now, except in one case with zirconia, we do not have flexible ceramics. So, sintering of these ultrafine powders is an issue. We have to have agglomerate free powders, because if we have got agglomerates as I have shown here, these will sinter very fast, and the next agglomerate which is over here would also sinter very fast. So, what we would have is, we left with is agglomerates which would first sinter themselves and then they would intersinter at much higher temperatures, as a result of which the very basic purpose for getting ultrafine particles, that is completely lost. However, people have developed methods so that this problem can be overcome. The next issue is sintering atmosphere. This is very important. Let us take the case of, say, very simple iron oxide. If I sinter it in air atmosphere, I will see grain growth, I will see sintering. But if I sinter iron oxide in a hydrogen chloride gas atmosphere, I will have grain coarsening only. It won't work. As I said earlier during the course of my lecture, the sodium vapor lamp, which is made from pure alumina powders, which is mixed with magnesium oxide as grain growth inhibitor, there the atmosphere used is hydrogen, so that oxygen can be abstracted, defects created, and sintering is enhanced. The atmosphere of sintering affects the densification rate very much. And let me last of all come to the impurities. They have a great role. They can be a sintering aid. Now, here is, I will make a complete distinction. A sintering aid can lead to formation of a liquid phase. That has been dealt with in the earlier lecture. Today, I am dealing only with solid state sintering. In that transparent lice housing of the sodium vapor lamp, a small amount of titanium dioxide is used. Titanium dioxide here helps abstract oxygen from the alumina in hydrogen atmosphere, leading to higher rate of sintering. This is one very well known case. We use such sintering aids in solid state sintering to a very large extent. Grain growth inhibitors, as I have talked of, play a huge role in ensuring that large scale grain growth does not occur. They have to be used wisely and carefully. And as a part of this sintering aid, we have to make sure that low melting phases are not generated during sintering, because as soon as these low melting phases are generated, they will remain. Chances are they will form a liquid phase, leading to a whale of a lot of problems. So, while sintering aids are an essential asset in solid state sintering by way of increasing the diffusion rate, by way of enhancing defect creation, and hence diffusion rate. You can argue that way. Addition of these sintering aids, solid state sintering, should be done carefully so that low melting eutectics are not formed. Now, I am aware that this is a very brief review, but I have kept it, brought it in because in ceramic fabrication, there are issues which need to be addressed. Before I end this review process, I have to bring in one more factor. Whether we are doing solid state sintering or liquid state sintering, we will use binders. Binders that will hold the ceramic particles together in the green state. Like say the chalk you use for writing on the board, that has got calcium carbonate and a very large amount of a gum. In ceramics, we do use such gums, of course, in very small quantities. We do use binders, and these binders will have to be burnt off. Normally, the polymers that are chosen as binders should be what we call clean burning polymers. The binders that are chosen should be clean burning, means when a polymer is burning, it tends to leave behind carbon. Now, this carbon can get trapped between grains. The carbon can get trapped. This carbon then can cause severe problems, because if it has got trapped, it has got nowhere to go, chances are it will abstract oxygen. In many systems, they will form carbides. So, while we are talking of solid state sintering, we have talked of particle sizes, temperature, atmosphere, sintering aids. We have to be very, very careful about what type of binders we choose. And by this, one has to really look at the thermogravimetric analysis, see how binders are burning, at what temperature they are burning. There is no one simple formula for binder selection. You have to go by experience and whatever takes it to get a proper binder so that sintering occurs properly. With that, I come to the end of review of sintering. What I shall take up next is phase diagrams in ceramics. This is what I shall take over. Let me start off with the first one that most of you are very familiar with, alumina silica, because that is where our ancestors started off. All of you are familiar with this particular phase diagram. You know this is the silica rich end, this is the alumina rich end. At this end, you have got silica plus mullite. At this end, you have got corundum plus mullite. And this is the mullitic zone. 3Al2O3, 2SiO2. Before I move on to three-phase diagram, let me point out one thing. The question, one, what happens if small amounts of Al2O3 is present in SiO2. This is A. And B, what happens when small amounts of SiO2 is present in Al2O3. This is the silica reagent. I presume all of you have studied ceramic technology. You have taken some, you have got some elementary knowledge of two-phase diagrams. And hence, you will notice that in this particular curve, this is the 100% silica end. I have said small amounts of Al2O3 means I am at this end somewhere. Notice the slope. The slope is pretty steep. Whereas on the other side, when we are talking of small amounts of silica and alumina, look at the slope, it is flat. What does it imply? It implies that if that alumina is more tolerant to silica, that is, if an alumina, even if a small amount of silica is there, significant decrease of melting point does not occur. But on the other hand, even if a small 1 or 2% alumina is there in silica, what we have is a sharp drop in the melting point. I use this diagram deliberately because to draft home this point, the slope of these curves say how tolerant is a system to the other. Let me move on. Now, you see the most of the ceramic materials that we use, whether it was 2000, 4000 years back or even today, they are not made up of A and B. There is AO or BO, A oxide and B oxide. Most usually we have got three components: AOX, BOX, COX, three different metal cations, if not more than three. So, I talked of liquid phase sintering. When I talked of liquid phase sintering, say what happens in porcelain, where we have got Al2O3, SiO2, and let me take calcium oxide. Here we have got three systems. System number 1 is Al2O3, SiO2. System number 2 is SiO2, CaO, and system number 3 is CaO, Al2O3. And we have, when we talk of sintering, we have to consider each system. I have already talked of SiO2, Al2O3. It looks like this. It generates, depending on the relative amounts of SiO2 and Al2O3, either it will generate corundum plus mullite if it is in the alumina rich end, or it will generate silica plus mullite if it is a silica rich end. Fair enough. So, we have dealt with here with the Al2O3 SiO2 system. What happens if I go to the next one? SiO2 CaO is a jumbled mass. I have deliberately drawn the full diagram because individual entities are not important. You see how many each of the red letters represent a phase depending on the composition. At the calcium ox, oops, sorry, I made a mistake. It should be CaO. At the calcium oxide rich system itself, we have got calcium oxide, and look at the different types of calcium silicates that are generated, the temperature falls. 1, 2, 3. Ca3SiO5 at higher temperatures, which becomes alpha Ca2SiO4, and at room temperature it becomes gamma compound. So here we are ending up with 1, 2, 3, 4. 4 different calcium silicates. Now, if this is a solid state reaction, because at these temperatures we are well below the melting point of CaOSiO2. So all of these are solid state transformations, all of which will take time. And hence, if I take CaOSiO2 in the calcium rich end, I may jolly well land up with 1, 2, 3, 4 products. Okay. At the silica rich end, it's much more interesting. At the silica rich end, which is over here, I will have cristobalite, which is the high temperature form of quartz which is stable, which will transform to tridymite, which is over here, and alpha calcium silicate. This is high enough temperature for transition to occur. But as I keep lowering the temperature and it becomes entirely a solid state diffusion reaction, this tridymite will convert to quartz, which is a time dependent process. Alpha CaSiO3 will tend to transform to beta CaSiO3. So we have got a wollastonite, which is a mixture of both alpha and beta. So now, if I am going to deal with a system where all of them interact, I have got to now work with mullite, silica, corundum due to Al2O3SiO2, and for SiO2 CaO 1, 2, 3, 4, 5, 6, 6 different chemicals, and this 6 is a reduced number because I took SiO2 as 1, though here I am showing SiO2 exists as cristobalite, tridymite and quartz, which are the different phase transformations. I am not yet through with it. The third system is CaOAl2O3. Look at the phase diagram of calcium alumina system. It's far worse. This is the calcium oxide rich end and this is the alumina rich end. How many compounds are formed? 1, 2, 3, 4, 5, 6, 7. And none of these existed in the alumina silica or the silica calcium oxide system. So now we are looking at 13 different chemical compositions which may be formed if I am looking at each individual two-phase diagram. Here I have got 3, here I have got 6, and here I have got another 6. In real life, when alumina, silica, calcium oxide are sintered in the solid state, what is it that we get? Now this is fundamentally a triangle. How it was done I will come to later, but let me take it as an example as to how many phases are formed. This is a triangle, equilateral, This end represents the 100% alumina phase. This end represents the 100% silica phase, and this end represents the calcium oxide phase. As we have got a mixture of aluminum oxide, silicon oxide, calcium oxide, we are mixing it together and then firing. Before I remove this page, you can see I have numbered certain areas. In fact, the numbers should increase. I won't increase it now. This is a two-phase liquid region. But other than that, all of it are solids. And I am yet to number any one of this due to various reasons. I have got 8 principally identifiable compounds. I talked of silica, cristobalite, tridymite, quartz. I have talked of mullite. I have talked of corundum, alumina. Look at this new product I have written, galenite, which is formed in this particular zone. What it represents, I will come to later. It's a compound of calcia, alumina, silica. Now note here, there is another zone here I have written as 5. This is written different from this. Both of them are compounds of calcia, alumina, silica. But galenite has 2 CaO. You have to remember galenite is 2 CaO, Al2O3 and 1 SiO2. Whereas anorthite is 1 CaO and 2 SiO2. Now one has to make sense of all of these compositions. And I have not yet put in 8, 9, 10, 11, 12, 13, because these are too complex to be handled in this brief lecture. So, how do we handle a real life ceramic system where we have, say, 3 different components, as I have been talking of, Al2O3, SiO2, CaO. These are 3 different systems. On this diagram, what I have drawn is, if you consider it, I have not yet done any 3-dimensional. This is the CaO SiO2 phase diagram. On this side will be SiO2 Al2O3 phase diagram. And on this side will be CaO Al2O3 phase diagram. 1, 2, 3, 4, 5, 6, 7. And that is exactly the number of phases you have over here. I merely transplanted this 2-phase diagram on this, in this fashion. How we do it? That is where I intend to come. These are called 3-phase diagrams. Now you see, the matter I am pushing in is, in most of the cases when we sinter, we will have each of them. Say when we try to manufacture silica, unless it is a chemical synthesis route, alumina will be present. When we try to make pure alumina from bauxite ore, SiO2 has to be present. Calcium oxide is also present in natural sources. Now, before I take up the subject of 3-phase diagrams, I want to emphasize on how they rapidly change. You see, calcium is a metal belonging to the, or a non-metal really, alkaline earth group. So is magnesium. I'll be fluctuating between the two. This is a phase diagram of the calcium alumina silica system. This is the phase diagram. I've only changed calcia to magnesia. and the range of products that are formed when MgO is present has drastically changed. Take a look at the calcium alumina phase diagram. See how many products can be formed. In magnesia alumina silica system, there are very much more fewer products. We do have the silica, we do have the mullite, which was there also in the calcium alumina phase diagram. We do have corundum, which is alumina. The newer phases which have been generated, which were or family of compounds which have been generated here are spinel, MgOAl2O3. Let me use this, spinel, MgOAl2O3. More importantly, sapphire, which is MgOAl2O3SiO2. Yes, I am talking of the sapphire, which is a gemstone. Cordierite, a very important zero expansion ceramic. It's a fantastic engineering material. That has not been generated. I'm just comparing side by side. In CaOAl2O3 system, I had galenite, I had anorthite. But in MgO system, I have got cordierite, 2MgO, 2Al2O3, 5SiO2. I have got sapphire, the gemstone, 4MgO, 5Al2O3, 2SiO2. And further, the number of phases or components, if you will say, that are present in the MgO SiO2 system are much lower. For engineering use, we have the mullite phase as a refractory material, the corundum is another refractory material, the spinel phase, this is at the backbone of most electronic materials, the sapphire phase, the cordierite phase. This is basically the MgO or the periclase phase, which is the backbone of basic refractories. And what we have is also this one. This is called the forsterite phase, which until a few decades back was a backbone of many electronic industries, with a composition of 2MgO SiO2. So depending on what system you have, you generate phases in ceramic systems. And the question comes, how do I combine systems which are so much at variance with each other, say alumina silica, CaOSiO2, CaOAl2O3 into one particular figure which can be understood, say this particular figure. The question is, how are these constructed, or how can we construct these? This is what I intend to do while introducing free phase diagrams. But before I do anything, let me take a blank sheet of paper. I have said they are represented by a triangle in two-dimensional space. How they are represented, I will come to later. Let us say there is a component A over here, there is a component B, and there is a component C. If you wish, I can put a name to it. Let me say this is SiO2, let me say this is CaO. if you wish, I can say this is Al2O3. Now, what does all this space represent over here? Let me take this particular point. What does this point represent? This point actually represents the composition. How? How do we determine? First of all, we drop a perpendicular on this axis from this point. We drop 3 perpendiculars. This is the simplest way of measuring. Let us measure physically the length. Let us say this is A millimeter, this is B millimeter, and this is C millimeter, mm. Let us presume these are all in millimeters. Now, fine. So, what do I do? Here, how do I know how much of it is A? Well, the fundamental rule is percent A. This scale, which is opposite this, gives you the percentage of A. B divided by A plus B plus C multiplied by 100, this is a percentage of B. And A gives percentage of C. That is applying the basic lever rule which you studied in two-phase diagrams. This length is proportional to the amount of A, this length is proportional to the amount of B, this length is proportional to the amount of C. That's one way of measuring. Another way of measuring would be, if I could take, say, again another fresh graph and say, hey, what does this point mean? What I could do is, I could draw this graph, also measure it differently. I draw a parallel line through this point, parallel to this. I draw a line parallel to the base through this, and I draw a third line which is parallel to this, so now we have 3 intercepts. You take any axis. Let me take this axis. Let's say this is A, I've forgotten what is what in the previous diagram, B, C. So here we have got segment A, which is this length, segment B, which is this length, and segment C, which is this length. So now what you have is, again what you can do is A plus B plus C, measure it in millimeters, meters, whatever it is. B 100%, this is one composition. A into 100% divided by A plus B plus C, this will give you another composition, percentage of another material, and C multiplied by 100% divided by A plus B plus C would give you another composition. So, another ratio percentage. This is the amount of B, this is the amount of A, and this is the amount of C. You just apply lever rule. And that should tell you what are the different fractions of the different phases. I am deliberately not going to write it here. You will have to look up books. They are freely available on the net also to determine this represents what, A, B or C. Which does what? I leave it to you to find out. These phase diagrams which I am drawing, the reason I bring them up is, you may ask, in solid state sintering, everything is diffusion controlled. So, what are the chances that so many phases will be generated? You see, as I go deeper and deeper into the phase diagrams, you will find that small amounts of liquid phases are generated. They get saturated and these materials precipitate out. So, what happens is sapphire, cordierite, all of these, they are not necessarily solid state diffusion. They may be assisted with small amounts of liquid phase, and hence we talk of these three phase diagrams not only from the point of view of solid state diffusion, frequently small amounts of liquid state being created, lots of phases being generated from the liquid phase. What I would like to say is, this phase diagram is composed of two systems, three systems, CaO SiO2, SiO2 Al2O3, CaO Al2O3. Fine. What I want to know, what is this 0.5? What is this 5 all about? All I drop is 3 perpendiculars. This is proportional to the amount of silica, this length is proportional to the amount of CaO, and this is this. So, I sum the lengths up and find out what is the composition. If you look at 4.4, the lengths of the perpendiculars would be entirely different. Which would reflect in the difference in composition between here and over here. With this, I will conclude this lecture and then take up how these three phase diagrams are generated.